Hi, I'm Scott. I'm working from NASA Goddard right now. You might have known that used to be at University of Tulsa. I'm on temporary leave from there, pursuing a senior NPP at NASA. So I'll be talking about the Harm code that you might have seen. Okay, so yeah, that was supposed to be going. So. It's not a numerical relativity code, so it's a little bit of a change of pace, but we do use it for relativistic systems. Actually, Dennis will be talking later about his exploits pursuing numerical relativity with Harm. But mainly, we've been using Harm to look at GR systems, but using matter that doesn't backreact on gravity. And this code's been designed to study accretion disks around single black holes originally, and now we're using it to study binary black holes. And this is just a ray trace image of one of these binary black hole simulations. And the number of people that have contributed to the particular flavor of Harm that we use is listed here. It's a growing number of contributors, and we're always looking for more avenues to use Harm and to develop it further. So, how many people have seen this page? Okay, I'm glad that you visited this. So you can download the 2D version of Harm. It's publicly available from this site, and also some conservative primitive variable solvers down here. So I did not write the original version of Harm, but what I did was I formatted it so that other people could read it easily. And so I put it on the web page. That was my contribution. I also developed these kind of primary tools. Okay. So even though the author list is Gavin, McKinney, and Toff for Harm3D, which came out 2003, the public version wasn't available until 2006 because it took me a few years to put it into palatable form. I only say this because making codes publicly available is challenging, and I commend people who do this. And I think there should be more of it. And I've certainly not necessarily carried that torch, but I would like to really maybe go into the fold more in the future. So basically, Harm3D came from the 2D version of Harm and also a 3D version of a Newtonian manuscript code called Ham that Charles wrote. So using those two codes, I developed a new code that had HDF5 support, parallelism, and had numerous other tricks folded in. So something we added was PPM support. But basically, if you compare these sorts of features to the codes you use, it's very sophisticated. But the sorts of things we try to work and develop on are applications and science output. So we don't have a large development team on this. It's basically me, but in the past, like 7 years, more and more people have tried to expand its abilities. So basically, we've looked at different coordinate systems, okay, and incorporate different spacetimes. So these are the equations that we solve. It's not a 3+1 Valencia formulation. It is just a 4D formulation. But we do break down. We use some sort of space-like hypercircuits, but we don't use the same 3+1 language inside the code. Okay, so you supply a core metric, and it can compute plasmas. Okay, and that's basically it. Some novelties are in the cooling functions. So we use optically thin cooling functions, but we're now pursuing more optically thick cooling functions like neutrino leakage schemes. So the reason why I'm talking now is that we're pursuing post-merger evolutions using Harm so that we can better resolve the rotational instability in post-merger products. So we paid attention to MRI resolution in our single black hole accretion disks quite a bit. This is actually, I think, the current record for the MRI resolution, this particular run. So this one passed with the largest quality factors, apparently. John Hawley and Julian Krolik looked at this a few years ago. And it requires a lot of zones in the radial dimension and in the azimuthal dimension. And we use grids that usually conform to the symmetries of our accretion disk, and that allows us to more efficiently resolve that MRI. So the aim is to carry forth with that knowledge and expertise and to see if we can actually develop dynamically powerful magnetic fields in these post-merger products. The value of Harm also is in the sibling codes that are associated with it. So Bathros is a post-processing geo-ray tracing code that can calculate the synchrotron or Bremsstrahlung emission from black hole accretion disks. Some of the functions inside Bathros were used in the Event Horizon Telescope codes. So you might have seen in the various papers something called iBathros. So a lot of the code development that went into Bathros went into those codes. And it's this is my way old. First 3D Harm simulation I did, I ray traced it, and this is my first picture of what Saturday Star would look like. But you know, they had to go in image in '87, so that was just but it looks actually pretty close. So apparently, optically thin black hole, optically thin gas around black holes, they all look more or less alike. So there's also so for the routines that we use for synchrotron, cyclosynchrotron emissivities are in this code called Harmony, and that code is actually used in the Event Horizon Telescope team. So, and we use fast light approximation, so the photons can move. They move faster than the gas flows, but we can also run it in the regime where the photons are moving with the motion of the gas. So we have to do time integration, interpolation between snapshots. So we've also, another sibling code is Pandurata. So Pandurata is a Monte Carlo tool that you use to scatter light in the corona of accretion disk simulations. And so we've used this to model spectra of X-ray binaries and to see how, if we dial the accretion rate, we can get different, we can get spectra that appear like the changes of state in accretion disks. We are now using this other code called PTransX. So Pandurata is Jeremy Schnittman's code. PTransX is a code written by Brooks Kinch, who's a graduate student, who's a graduating student from Johns Hopkins. It's part of Julian Krolik's PhD supervisor. And so PTransX, what it is a photoionization code that performs hour-long calculations of photoionization balances. So it looks at the species of elements and sees what the radiation field, how it will ionize those elements. And then that gives you the albedo of the disk. Okay, so it tells you how radiation is reflected off of it. And so that is important because in order to get accurate, energy resolution in your resultant spectra, you need this information. So, for instance, you need this information if you want to calculate the iron line profiles of these accretion disks. So, iron lines are obfuscate fluorescent lines. So these are lines that are used to measure black hole spins. And so this is just an example of how they've used PTransX with Pandurata using Harm data products. We're now trying to wrap this all up together. So even though we're not running Pandurata and PTransX coupled in a dynamical simulation of Harm, we want to, as a step towards that, we're trying to simulate what Pandorata does, cools the corona. So in order to calculate the Compton cooling or heating in the corona, you need to measure the local energy density of the photon field. And so one simple way we're doing this right now is to just assume flat space geodesic integration, so straight lines, right, from the photosphere. And then so at every coronal point, we integrate the flux over the photosphere. So this is, an order, it's the n to the 5th, where n is the number of cells per linear dimension kind of operation, so it's kind of expensive. Okay, so but that allows us to measure the local photon field energy density, and it gives us a coronal cooling rate that we use then in a dynamical simulation. And then so some evidence that this is working is a snapshot about a spinning black hole at 0.5. We see that the temperature this is the cooling rate, of a meridional slice through the disk, and we see that there's a lot of cooling right above the photosphere, and that's because the radiation field is the strongest there, because it's close to the surface, right? And so this is just to give you a flavor. And so we tune it to an edited factor, and this method tracks our goal editing factor here. So we're now wanting to couple all of these codes together so that we can do Monte Carlo radiation transfer in a corona, have some sort of photoionization balance in deep in the disk, and then it matched to some Harm simple cooling function in at tens of optical depths, where X is too expensive. So we're exploring this now. This sorts of machinery, though, is applicable to neutrino disks, right? So disks from neutron star mergers. And so we're going to be leveraging our experience in this regime to the neutrino regime. Many of the processes operate in the same way between photons and neutrinos. And this is a schematic of how we're approaching this. So Harm has to somehow apply a more accurate radiation field, and that informs P-Transx and Pandorata calculations. The P-Transx then gives a better result of the cooling rate locally, that then informs how the plasma evolves. So I mentioned before, we pursued different coordinate systems. So one coordinate system that we were interested in, something that could resolve the plasma accurately near black holes. So in spherical grids, it's not applicable to binary black holes, because you need a lot of cells near each black hole. So you have to kind of pinch the spherical grid near each black hole, but we want it to asymptote to spherical. A spherical topology, because the circumbinary disk follows circular paths, Keplerian paths around the inertial mass of the system. And so that allows us to conserve angular momentum really well out in the circumbinary flow, but then also resolve the MHD dynamics near each black hole. So this is just an animation showing you how we can control the local resolution through parameters, mass ratios. So right, as you get a larger mass ratio, the center of mass goes closer to the original. All right. So we tested this method out. So this is an advective field loop, and this shows you how dissipative this moving mesh. It's not a moving mesh. It's a dynamically distorted mesh affects the MHD evolution. So you see that the high resolution actually does lead to less dissipation in the field, and so it seems to be doing really well. And this is just going through a symmetry point, right? This line is identified by this line, and where that gets a little confusing. So we've used this in binary discrete and binary black hole space times. This is a hydrodynamic proof of principle calculation that we did early on. This movie goes on for a long time, but I just want to highlight how well the disk satisfies its spherical symmetry or axisymmetric symmetry for a long time. Right? If you did this in Cartesian coordinates, you would immediately get these accretion streams formed from the inside of the cavity. Okay? And because so much attention was paid towards computational efficiency earlier in this conference, I just want to say that we pursue task management ideas as part of our PRAC. So this was part of the NSF paid program, the sub-award to the PRAC. And we, this is part of Blue Waters at NCSA. And so in our binary spacetimes, computing the metric near the black holes is more expensive than computing it further out in the wave zone or in the near zone, where you just evaluate the post-Newtonian metric. But the inner zone here is more expensive. And so you want to break up that inner zone more, and then parcel out to fewer computing cores. And here this shows you how much more expensive, how much more time some cells spend in computing the metric than others. Okay, so there's a load imbalance. We want to distribute that load imbalance and even it out. And so one way of doing this is to use AMPI, adaptive MPI, which is part of the Charm++ suite. So each MPI task is a AMPI task, and you can put many, these are called virtual processes, and you can put any number of virtual processes on a specific node. So some nodes may have 2 VPs, while others may have 32. So that's how you load balance. When we found that the theoretical advantage that we would expect from this was a 20% gain. We only got about a 10% gain. And it required a great deal of recoding. I think actually this sort of exercise was fruitful. So what we had to do is we had to wrap all the global variables inside a structure that we then passed to all of the routines. And that allowed any heap, any process, virtual process, to be able to be transferred to another core. Okay, so all of its memory that was associated on the subdomain could be transferred to another core, another node easily. And this just shows you how that load imbalance evens out as the number of time steps has occurred. So if you want more information about this, so we only got a 10% gain because there's some overhead in using AMPI. And also, if the load imbalance wasn't so great, if it was even greater, then we would expect even better gains. So yeah, so what we've been doing is we've been doing binary black hole accretion simulations with MHD. We've been using this warped grid, and it's allowed us to simulate how mini disks around each black hole interact, how the magnetic field lines from these disks emanate, how the mini disks interact with the circumbinary flow, and yeah, so I think it's been helpful. You can also dynamically alter. Not only can you move little local high-resolution spots around, but you can also shrink grids. So here, this was just a circumbinary disk simulation that Mark Navarro did, where he excised the region where the black holes are to accelerate the simulation to use its larger step size. But the black holes started off at a separation around 42 n, so very far out, allowed it to inspiral to I guess 10 n, but the grid, since it was truncated outside the orbit of the black holes, it had to move in with the black holes as they inspired. And so that's what he did. So the grid would adaptively, slowly, secularly shrink and track the inner edge. And we're also using this for tidal disruption events, so we can use kind of the frame agnostic, coordinate agnostic framework in Harm, and we can move the domain with a moving star in a background space-time and see how it's tidally disrupted as it transits close to a black hole. And this is work that Teho Liu and Julian Krolik are doing at Johns Hopkins. And the idea is to eventually, so this is a movie by Rosanna Chang did a few years ago, is to put that patch inside of a larger patch using this patchwork code that we've been using, and to then see how that debris, that tidally disrupted debris, then forms an accretion disk. For the post-merger project, we hope to do long-term, maybe second-long timescale simulations of the post-merger products. And in order to do that, you need to really resolve accurately the jet region very well if you want to maybe simulate the GRB jet that forms, that possibly forms from these systems. And so spherical coordinates are not so great on the axis. So one way to remove the coordinate singularity there is to cover it with a patch. So what we've done here, Mark showcased 2 days ago, is that he used a tilted spherical patch to cover the region around the polar axis. And that allowed him to study black hole, creating black hole with a jet, and without any sort of numerical artifacts near the axis. And so we're repeating the circumbinary accretion problem with mini disks using this patchwork simulation. I also showed this movie. I just want to repeat it here. You know, you don't see any sort of grid interface effects, so it seems to be working pretty well. And there's been some discussion about code comparisons, and the Event Horizon Telescope team encouraged the greater GRMHD community to compare the same run to each other and to see what the dispersion is in the simulation results over the coast, to kind of arrive at some sort of systematic error in the GRMHD simulations that are used to produce images that are then used to compare to the VLBI observations that they made as they had to do for this really remarkable discovery of the first picture of the black hole's event horizon, or the gas around black hole. So I think the numerical relativity community, I know that there have been efforts in the past to do head-to-head comparisons of specific initial conditions, evolutions from specific initial conditions, but we could maybe learn from this experience and develop something similar. And I just want to say that, thank you for your attention, and Harm is all of these, and we're going to be using it to try to resolve the MRI near these nascent black holes that form out of neutron star mergers. And these are kind of my to-do list. So I'd like to include higher order methods, and I'd like to include OpenMP and GPU support. There's this thing called, I don't know if you all have heard of this COCOS thing. You can implement these directives, like OpenMP directives, and it takes care of the GPU deployment for you. So that sounded really easy and exciting, and I have no idea how useful it is, but just want to throw it out there, and thanks.